Lava pressure is building beneath Washington state right now, and scientists have just found something buried under the ground that is rewriting everything they thought they knew. Deep below the forests, deep below the cities, deep below the 4 million people living in the Pacific Northwest, the Earth's crust is cracking apart. Not at the edges where geologists knew to look, but from the inside. And when rock splits open miles underground, something starts moving through those cracks. Upward. Heat signatures appearing where there should be none. Volcanic gases spiking at sensors that have been silent for years. A swarm of strange earthquakes forming patterns beneath the surface that veteran scientists are calling unlike anything in the historical record. The last time pressure built like this beneath this exact region, the coastline vanished underwater in minutes. That was 1700, before a single city existed here. So here is the question that is keeping geologists up at night. Is a hidden volcano already emerging beneath Washington? And will we know about it before it's too late? The Cascadia subduction zone is one of the most dangerous geological structures on the planet. Stretching more than 600 miles from Northern California all the way to British Columbia, it is the place where the Juan de Fuca plate grinds beneath North America in a slow, relentless collision that has been building pressure for centuries. For decades, scientists treated Cascadia primarily as an earthquake threat. A locked fault. A sleeping giant. Dangerous, yes, but at least predictable in its mechanics. You watch the boundary. You measure the stress. You model the rupture. That assumption is now gone. Recent advances in seismic tomography and ocean bottom seismometers have given geologists an unprecedented view into the subduction machinery operating miles beneath the Pacific Northwest. Ultra-sensitive instruments buried on the seafloor are detecting faint tremors, subtle shifts in gravity, and slow tilting of the land above. Pieced together, these signals reveal something that no geological model anticipated. Cascadia is not merely locked and straining at its boundary. It is fracturing internally. New cracks are forming within the subducting plate itself, not at the edges where scientists knew to look, but deep inside the rock. The skeleton of the continent is bending and breaking in ways that geological science has never documented in real time. Dr. Harold Tobin, director of the Pacific Northwest Seismic Network, describes the data as watching a geological rule being broken before our eyes. But here is where the volcanic threat enters, and why it changes everything. Washington's Cascade Mountain Range is not just a chain of scenic peaks. It is a volcanic arc, built entirely by the heat and pressure generated by the subduction process directly below it. Mount St. Helens, Mount Rainier, Mount Adams. These volcanoes exist precisely because the Juan de Fuca plate sinks beneath the continent, releases superheated fluids, and melts the rock above, feeding magma chambers that have been quietly recharging for years. When the subducting plate fractures internally, it does not simply redistribute seismic stress. It reorganizes the entire underground plumbing system. New fractures create new pathways, and what travels upward through new pathways in volcanic terrain is not water. The mountain did not move, but the ground beneath it just did. Off the coast of Washington, seismic data is revealing something that sounds like science fiction. Kilometer-long fissures are venting fluids and gases from within the subducting plate. Deep cracks are still widening. Swarms of micro-earthquakes echo through the dark at depths that rule out any surface explanation. The crust here is up to 20 miles thick, built from countless layers formed over millions of years, and it is peeling apart from the inside. University of Washington geophysicist Dr. Alicia Mendez studies the thermal imaging overlays and underlines the same cluster 3 times. An anomalous heat signature is blooming upward from the fracture zone. Not a volcanic vent, not a mapped fault. Something new, something that was not there before. For volcanic systems, this matters enormously. Normally, magma rises through established conduits, well-mapped pathways formed over millions of years of eruption cycles. Every monitoring system in the Pacific Northwest is calibrated to these known routes. USGS seismometers, GPS ground deformation sensors, volcanic gas detectors, all of them tuned to watch the doors that geologists already knew existed. But when the crust splits open, new doors appear. In recent monitoring cycles, both ground swelling and minor increases in volcanic gases have been detected near several of the region's major peaks. At one station on the southwestern flank of Mount Rainier, a volcano sitting directly above a metropolitan area of 4 million people, sulfur dioxide readings have ticked upward across 3 consecutive measurement periods. Not at alarm levels, not yet. But the direction is unmistakable. And in a system this large, this interconnected, and this poorly understood, a trend that has no explanation is not something you dismiss. It is something you watch with growing unease. At the Pacific Northwest Seismic Network Operations Center in Seattle, analysts cross-reference the volcanic gas data with the new fracture mapping from ocean bottom instruments. The overlap is not reassuring. Dr. Seth Moran, scientist in charge at the USGS Cascades Volcano Observatory, chooses his words carefully. He does not say eruption. He says heightened complexity. He says evolving system. He says the monitoring picture looks different than it did 5 years ago. In volcanology, heightened complexity is not a reassurance. It is the warning that comes before the warning. And right now, every sensor pointed at this region is saying the same thing. To understand why a splitting crust creates volcanic danger far beyond the known peaks, you first have to understand what Washington actually is, geologically speaking. Most people picture it as solid, ancient, immovable ground. The foundation beneath their homes and cities and farmlands. Something permanent, something reliable. That picture is wrong. Washington is not one solid piece of continent. It is a jigsaw. Dozens of ancient fragments, microcontinents, slivers of seafloor, chunks of volcanic island chains, all fused together by hundreds of millions of years of collision, grinding, and upheaval. Much of eastern Washington was once a string of isolated volcanic islands drifting in the open Pacific Ocean, slowly carried eastward over millions of years until they collided with North America and were welded into the continent's edge. The forested hills and mountain slopes that look so permanent today are, quite literally, scraps of lost worlds. And every seam between those ancient fragments is a scar. And scars, under pressure, crack first. As the Cascadia fractures spread and stress migrates through the region, these old buried boundaries are being reactivated. Faults that have sat completely dormant for centuries are showing fresh signs of movement. The geological map that emergency planners and engineers built their entire risk models on is becoming incomplete in real time. What was considered stable ground yesterday is being quietly reclassified today, and the communities sitting above these reawakening seams have no idea that the map beneath their feet is being redrawn. For volcanic hazard, this is specific and alarming. Washington's volcanoes are not isolated features sitting independently on the landscape. They are the surface expression of a deep, interconnected system of heat, fluid, and magma threading through the entire crustal patchwork below. When new fractures reactivate old seams, they do not just generate earthquakes. They create new migration corridors for volcanic fluids, the superheated water, carbon dioxide, and sulfur compounds that move ahead of magma, like scouts before an army. Dr. Carolyn Dradger, a USGS hydrologist who has spent 2 decades studying the fluid systems beneath Mount Rainier, describes the new fracture activity as introducing variables into a system that was already dangerously under-monitored. The ancient wounds beneath Washington are not healed. They are opening, and something is moving through them. In January of 1700, the Cascadia subduction zone ruptured in a full margin earthquake estimated at magnitude 9.0. The shaking lasted 4 to 6 minutes. The coastline of the Pacific Northwest dropped several feet in seconds. Entire forests drowned in salt water as the land itself sank. And then the ocean pulled back from the shore, the way it always does before a tsunami arrives. The wave that followed crossed the entire Pacific Ocean in 8 hours and struck Japan with enough force that government officials recorded the arrival of a mysterious, sourceless wall of water. That Japanese record became the timestamp that modern scientists used to pinpoint the exact date of a disaster that left no written history in North America, because there was nobody here writing history yet. Standing dead forests preserved in coastal marshes. Sudden sediment burial layers visible in cliff faces along the shoreline. Tree rings that stopped growing in unison across entire hillsides in the same year. These are the clues that survived. These are the warnings the Earth left behind for anyone willing to read them. And what is happening now is more complicated than what happened then. In 1700, The rupture ran along the main locked boundary, the contact zone between the two plates. Catastrophic, but mechanically familiar. Scientists have spent decades modeling that specific scenario, refining evacuation routes, calculating tsunami arrival times, mapping the shaking zones. But today's fractures are different. They are forming inside the subducting plate, not just at its outer edge. This means a future Cascadia event may not follow the script that emergency planners have rehearsed. It could rupture in multiple segments simultaneously. It could jump between fracture zones in sequences that current models were never designed to predict. And it could interact with the volcanic pressure building beneath the surface in ways that the 1700 event never did. Because in 1700, the crust was not also splitting apart from within. USGS geologist Dr. Brian Sherrod, who has spent years mapping buried fault systems beneath the Puget Sound, describes the new intraplate fracturing as adding a variable to every existing disaster scenario that nobody has a confident answer for yet. The question facing the Pacific Northwest is no longer simply when the next Cascadia earthquake will occur. The question is what kind of event it will be, how many systems it will touch, and whether the volcanic pressure quietly building beneath Washington will be part of the answer when it finally comes. For years, seismologists tracking the Pacific Northwest worked with a known cast of characters: the Cascadia megathrust, the Seattle Fault, the South Whidbey Island Fault. Dangerous, well-studied, and at least partially understood. Emergency planners built evacuation routes around them. Engineers designed buildings to withstand them. The entire regional risk framework rested on the assumption that the dangerous places were already identified and mapped. Then the strange earthquakes began appearing in places that were not on any map. Deep beneath the Olympic Peninsula, a series of faint, slow-moving seismic signals started showing up on monitoring networks. Not typical earthquakes, but episodic tremor and slip events forming along new crack pathways at significant depth. Hundreds of these micro-tremors occurring in waves, weeks apart, at locations that correspond to no known fault line. They are too deep for surface causes, too organized for random noise, and too consistent to be dismissed as instrument error. Beneath the ocean floor off Washington's coast, seismometers are now recording intraplane earthquakes, quakes originating not at the plate boundary where scientists always focus their attention, but within the interior of the subducting Juan de Fuca plate itself. In the language of seismology, this is deeply abnormal. These events are not supposed to happen here, and yet they are happening with increasing frequency. Each unexpected event does two things simultaneously. It releases stress in one location and transfers it somewhere else. Scientists have observed that moderate offshore earthquakes can sometimes trigger movement on inland fault stays or even weeks later. A chain of stress migration, connecting the offshore fracture zone to the volcanic arc above it to the populated valleys sitting between them. The system is linked in ways that older models never fully captured. At the Pacific Northwest Seismic Network, analysts now maintain a dedicated monitoring thread specifically for intraplate events, a category that barely existed in their daily workflow 3 years ago. Dr. Maximilian Werner, a seismic hazard researcher who consults on Cascadia risk modeling, describes the current picture as a system revealing its own complexity faster than science can absorb it. The volcanic consequences compound the seismic ones directly. Every new intraplate fracture is a potential fluid migration pathway. Every fluid migration event carries heat deeper into the crust. Every heat transfer shifts the pressure balance inside magma systems that are already, by direct measurement, in a state of elevated and accelerating activity. The earthquakes appearing where none appeared before are not curiosities to be filed away. They are the map being redrawn in real time. And the new map includes volcanic risks that no current hazard plan was ever written to address. At the USGS Cascades Volcano Observatory in Vancouver, Washington, a bank of monitors tracks ground deformation, gas emissions, and seismic activity across all 5 major Cascade volcanoes simultaneously. The screens are almost always quiet. That is the baseline. That is what normal looks like in this building. Scientists here have spent careers watching these screens stay still, logging the unremarkable data, and waiting for the system to speak. Over the past 18 months, 3 of those screens have been slightly less quiet than usual. Ground uplift measurements near Mount St. Helens, the volcano that last erupted in 2004 and catastrophically in 1980, show millimeter-scale inflation in a pattern consistent with fluid movement at depth. Not magma intruding toward the surface. Not yet. But the pressurized, superheated fluids that precede magma migration in every eruption sequence ever recorded. The fluids that arrive first. The fluids that prepare the way. Sulfur dioxide readings at a sensor array on the eastern slope of Mount Rainier have shown a statistically significant upward trend across multiple consecutive measurement cycles. Scientists are careful to point out that a single elevated reading is noise, an instrument fluctuation, a bad data day. But a trend sustained across months and multiple independent sensors is something else entirely. A trend is a signal, and this signal has not reversed. Most striking of all is a cluster of micro-earthquakes detected in a zone situated between Mount Adams and Mount St. Helens, an area with no surface volcano, no mapped volcanic system, and no historical record of volcanic activity whatsoever. The depths at which these quakes are occurring suggest heat and fluid movement, rather than tectonic stress alone. Something is generating energy in a place that was not supposed to generate it. Dr. Margaret Malone, a research seismologist who spent 3 decades at the University of Washington studying Cascade volcanic tremor, reviews the Adams to St. Helens cluster data and describes it as the kind of signal that deserves serious attention and a great deal more instrumentation pointed directly at it. That is the careful, measured, scientific way of saying we do not fully know what is down there. And in geology, the zones of greatest uncertainty are not automatically the zones of lowest risk. Sometimes they are simply the zones of greatest danger that have not yet been given a name. If a hidden volcanic system is already building pressure beneath Washington's surface, fed by new fracture pathways and driven by stress migration from a splitting subduction zone, the first warning may not come from any volcano currently on the map. It may come from somewhere nobody was watching at all. Seattle sits on the Seattle Fault, a shallow crustal fault fully capable of producing a magnitude 7.0 earthquake entirely independent of anything happening at Cascadia. Directly to the south, Tacoma occupies the lahar corridors that drain from the slopes of Mount Rainier. The Puyallup Valley stretching between them is home to 80,000 people and sits in the direct path of debris flows that USGS models calculate could travel at 40 miles per hour with no meaningful warning. These are not remote wilderness risks. These are the neighborhoods where people are dropping their children off at school this morning. Compound disaster scenarios, megathrust earthquake followed by volcanic fluid release, followed by lahar, followed by tsunami. Striking the coastline are no longer theoretical exercises confined to academic research papers and geology conference presentations. They are what emergency planners in Pierce and King counties are quietly beginning to wargame behind closed doors. FEMA's Cascadia Rising exercise, conducted in 2016, modeled the regional response to a full Cascadia megathrust rupture along the known boundary. The conclusions were deeply sobering. Infrastructure failures cascading across 140,000 square miles, 13,000 projected casualties in the immediate aftermath. Full recovery estimated at 1 to 3 years for some communities and potentially decades for others. The exercise shake everyone in the room who participated. And that exercise did not model a hidden volcanic system activating at the same time. It did not account for new fracture pathways reorganizing the underground plumbing of the Cascade volcanic arc. It did not factor in the anomalous heat signatures now appearing between mapped volcanoes. It did not include the possibility of magma pressure building beneath a location that carries no warning label and appears on no hazard map currently in use. The new fracture data, the volcanic gas trends, and the unexplained seismic clusters beneath the Pacific Northwest do not constitute proof that a hidden volcano is emerging beneath Washington right now. Scientists are honest about that. The data raises questions that cannot yet be fully answered. But the people who watch this data every single day are using words like unprecedented, evolving, and unknown with increasing frequency. And those words are not abstractions to the 4 million people living directly above this system. The ground beneath Washington is changing. The science is struggling to keep pace. And the window to understand what is coming before it arrives is narrowing faster than anyone in this field is comfortable admitting. The fractures forming in the dark beneath Washington's ocean floor are not slowing down. The heat signatures blooming upward through rock that should be cold are not disappearing. The micro-earthquakes appearing where no fault was ever mapped are not stopping. And the volcanic gas readings that keep moving in the wrong direction at sensors across the Cascade Range are not reversing. None of this is proof that an eruption is imminent. Scientists are careful to say that, and they are right to be careful. The Cascade volcanoes have shown periods of restlessness before, and quieted again without incident. Geological systems operate on timescales that make human memory look like a single breath. A signal that looks alarming across 18 months can sometimes resolve into nothing across 18 years. But something is different this time. And the difference is not one anomaly in isolation. It is the convergence of multiple independent signals, the intraplate fracturing, the stress migration, the anomalous heat, the volcanic gas trends, the unexplained seismic clusters, all pointing in the same direction at the same time. Scientists can dismiss one outlier. They cannot easily dismiss all of them simultaneously. The Cascadia subduction zone is transitioning into a phase of behavior that has never been recorded in the history of modern geology. The crust is splitting in ways that are reorganizing the volcanic plumbing of an entire mountain range. A hidden system may already be building pressure beneath ground that carries no warning label and appears on no evacuation map. 4 million people wake up every morning above this. They drive the same roads, send their children to the same schools, and trust the same ground that has always held them. That trust is not unreasonable, but it was built on a picture of this region that is no longer complete. The secrets beneath Washington are becoming visible at last. The question that remains, the one that keeps researchers at their monitors long after their shifts have ended, is whether we are watching this transformation early enough to matter. Because in geology, the only thing more dangerous than a system that is breaking apart is a system that is breaking apart while nobody is paying attention.